Hello, welcome back. So we figured out a buffer made of a weak acid and its conjugate has a pH, okay? And it has a pH that's not neutral. It depends on the buffers and the K values and all sorts of other things. So now what we're going to do is we're going to see, does the buffer do what we want the buffer to do? Does it resist changes to pH? That is going to be our trial now. So let's start first by looking at what happens when we add a strong acid to water. So we're going to start with 100 milliliters of water. We're going to add 1 milliliter of 1 molar HCl to that water. And I'm not going to show you the calculations or anything like that. This is just a dilution calculation, right? M1V1 equals M2V2. pH is 2.0. Okay, so you take 1 milliliter, like beep, 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 and add it to 100 milliliters of water, and boom, the pH drops from 7 down to 2. Huge, huge changes. Now, on the other hand, I've got a big beaker full of 10 liters of water, and I add my 1 milliliter of 1 molar HCl to this. Am I going to get the same thing? Is my pH going to go all the way down to 2? If you're a little on the fence about that, think about if I added it to the world's oceans. 1 milliliter of 1 molar HCl added to the world's ocean is going to take the pH of the ocean from 7 down to 2. And you're like, of course not, it's the ocean. So if it works on the ocean level, it also works on a smaller level. So going from 100 milliliters to 10 liters, if that 1 milliliter does nothing to the ocean, it should do a little bit less to 10 liters than it does to 100 milliliters. And if you do the dilution calculation, you should find that here the pH is 4.0. Okay, so there is a major change in terms of pH and things like that, depending on the total amount of stuff that we add and how much we add it to. So as we do some of these calculations with the buffers, these total amounts are going to matter in a way that it often works better to do some of the stoichiometry and stuff in moles. And so we're going to find that that is going to be an easy way to do things, is to do some stoichiometry in moles. And we'll see when we do it and when we don't, just by example over time. So let's go ahead and say we've got a 1 liter solution, and it contains our 0.500 molar HAC, and it contains our 0.500 molar AC minus, and we're going to add somehow 0.01 moles of HCl. Notice I'm not adding a volume here. I'm not changing the total volume. Even if I added a milliliter, it wouldn't matter so much. How do we do that? One, in practice, you never actually do that, but you could. You can actually take hydrochloric acid, which is a gas, and bubble it through a solution. And it'll mix with the solution, it'll add acid to the solution, but it won't change the total volume. So it's technically possible, people do it all the time for example purposes, to not change the total volume, and that's what I'm doing for you guys. So what we're going to do is see what happens to pH. We figured out in the last slide that the pH of this buffer solution was 4.74, and so let's see what happens to the pH when we do this. Well, this is also just some sort of problem where we've got a bunch of concentrations, they change over time, and then we solve for that. So let's try to set up our good old ice table here. HAC goes to H plus plus AC minus. We've got I, C, and E. The H is 0.500 moles. So I'm going to use moles now as my unit. In my ice table, I almost always put a unit on the first number and usually on the first row just to remind myself what the units are that I'm using. I've got 0.01 moles of H plus. I've got 0.500 moles of AC minus. All right, so now we've got this issue, right? We've got everything there. How do we know which direction this reaction is going to run? How do we know? Is it going to go to the right or is it going to go to the left? What tells us what happens to a reaction when we're not sure it's at equilibrium? And if you came up with Q, you were paying attention. All right, we can calculate Q for this guy, and it turns out that Q is 0.01. So if you remember that our K was 1.8 times 10 to the minus fifth, then you realize that Q is much greater than K, and so the reaction is actually going to go to the left. And so we say 0.500 plus x on our left minus x on our right, right? Which is not what we've been doing up till now, right? We've always been doing plus x's on the right, so this is slightly new. Ooh, okay, but we just calculated it from Q. 0.500 plus x, 0.01 minus x, 0.500 minus x. All right, let's go ahead and plug that into our K. Ka is h plus ac minus hac. Do you think the world should be a musical sometimes? 1.8 times 10 to the minus fifth, and that's going to be 0.01 minus x, 0.500 minus x, over 0.500 plus x. All right, we've got some pretty good orders of magnitude difference between our concentrations and our K value, so we might think about, hey, small x assumption in this case, but if you take out all those x's, there's nothing left to solve for, and you end up with that 0.01 is equal to 1.8 times 10 to the minus fifth, and that's not quite what we're looking for. So we have to be a little more judicious in our use of the small x assumption here. And what we're going to say is we're going to say x is small, much, much smaller than 0.500, but perhaps it's not that much smaller than 0.01. And so we're going to see what that assumption looks like. Okay? So this turns into 1.8 times 10 to the minus fifth is equal to 0.01 minus x times 0.5 over 0.5. Cross out. And we get that 0.0, or 1.8 times 10 to the minus fifth is 0.01 minus x. Right? 1.8 times 10 to the minus fifth is 0.0000018. Okay? This one, even if we had one more significant figure, which I probably should have been writing down, 0.010 minus 0.000018. If you do your significant figure rules, that is 0.010, right? You know, you can't keep track of the significant figures of the 1.8 times 10 to the minus fifth because it's so small. So you get that x equals 0.010, and therefore the concentration of H plus is 0.010 minus x, which is 0. Wait, what just happened here? What just happened here? How did we get a concentration of 0? Like, the H plus just disappeared. Now we have a pH of 7? That's kind of strange, don't you think? What happened here? Well, maybe our assumption wasn't so good, right? Our assumption of 0.01 compared to 0.5 wasn't so good. Let's plug that into our calculator. We say a 0.01 divided by 0.5 times 100. 2%? Hey, that's within our valid assumption for, Now, it turns out if you go ahead and ignore your significant figures, right, if you ignore the fact that we don't have the significant figures to subtract 1.8 times 10 to the minus fifth, you actually do end up, I say, if we ignore sig figs, then you do actually end up with that the H plus is 0.000982, 9.82 times 10 to the minus third, and my pH is 4.74, which, hey, that's no change to pH. I added a small amount of acid and I got no change to pH. That's great. That's exactly what I was looking for, right? That I have something that resists changes to pH. But in order to solve that problem, I had to ignore significant figures. And if you think chemists are going to be okay with a problem that in order to solve it, you need to ignore significant figures, you need to think about significant figures more. So there's something not quite right. Now, of course, this is just a simple quadratic equation, so I could totally just plug this in, use my Wolfram alpha, or I could even just use the quadratic equation and solve this. And if you solve it exactly, you get a pH of 4.73. All right. So you do either get no pH change or you get a very, very small pH change. And I know that that really upsets someone in the background. They're very sad about the fact that pH isn't changing. But that's what happens. The pH doesn't change all that much. But we do have to figure out a way around that problem where we're like, hey, in order to solve this easily, we have to ignore significant figures. Let's see if we can figure out a way around that. How do we skirt that sig figs problem? And the reason we have a significant figure problem is not because the problem itself is flawed, but because of our solution to it is flawed. We are ignoring the chemistry. Remember, when we're looking at K expressions, we're looking at equilibria. We're looking at stuff that goes left and stuff that goes right, and it's a balance, and it goes back and forth. Something's reacting with this, something's reacting with this. We're making reactants, we're making products, and it all is just fine. But when you have a strong acid, right? I added HCl. I've got a bunch of excess H plus floating around. Remember, my pH could have gone down to 2 if I had this in a 100 milliliter solution. So if I've got a bunch of H plus around, then I don't have equilibrium, right? H plus is a strong acid. It is looking for things to react with. So as soon as that H plus sees that AC minus, it's going to react in one direction to form HAC. Right? Because we have excess, we have lots of H plus around, and so it's going to find things to react with. And when it finds things to react with, it's going to make some HAC. So it turns out, in order to solve this problem, we have to keep in mind the chemistry. And we'll see this in the future too. We'll see this in the next chapter when we're talking about complex ion formation. Anytime there is a strong reaction, I'm going to write this down, anytime there is a strong reaction, right? And this is when you have excess H plus or OH minus, or when you have a very large K, right? And you've got only reactants, right? Then the K is really going to go, and it's going to react first. We'll see that later on. But for now, we're talking about anytime you've got excess H plus or excess OH minus, you have to get rid of that first. You have to run that strong reaction. Get rid of the things that are not equilibrium before you do equilibrium. So you must run the strong reaction before doing equilibrium. All right, so you must run that strong reaction before you do the equilibrium. So if we have 0.01 moles of H plus, we have to react that H plus before we do our equilibrium. So I'm going to write down the same thing we had before. HAC goes to H plus plus AC minus. But now, since I know I've got these amounts here, 0.05 moles, 0.1 moles, and 0.50 moles from our last slide. This is not an equilibrium expression, so I'm not going to start with ICE. I'm not going to start with initial change and equilibrium. I'm going to do what I call a Brice table, which is anytime I've got a strong reaction, I've got before the strong reaction, I've got the reaction itself, and then I get my initial concentrations, which then undergo equilibrium. So this is my equilibrium portion. This is my strong reaction portion. And again, strong reaction is I've got excess H plus, I've got excess OH minus, or I've got a really large K and reactants that will react, or and also a very, very small K and I've got products that might go backwards. So if I'm going to react my H plus, I'm going to react as much as humanly possible until I get rid of it. I don't want to have excess H plus around because H plus is a strong acid, right? Tiny amounts of it, it's not so bad, but I've got a huge amount of it. So I want to get rid of that. So I want to try to see if I can react all of my H plus. Now, if I ran out of AC minus, I couldn't react all my H plus, okay? But I have plenty of AC minus here, and so I'm going to react all of that. And of course, on the other side, if I reacted on that side, I've got to make it here. Now, you'll see lots of people who do this without this kind of official table and things like that. And even some of the examples I'm going to do later on, I might not use this table. But one of the reasons I like having this table is this spot here reminds you that when you use up the H+. When you use up the AC-, you are making something else. It's so easy to forget, and it changes your answer. It changes the pHs that you get in your solution. And it's wrong, so you know that too. So now we do our little stoichiometry, and we get 0.510 moles, and we get 0, and we get 0.49 moles. I should probably take my digits down there. All right, so there we go. So now I've got my numbers here, and since I have no more excess acid, now I have an equilibrium problem with only slightly changed amounts of my H+, or my HAC and my AC-. So now I can do my standard ice table, the one we've seen so many times. We can write that into our Ka expression. And you're like, Professor Clemens, why are you still writing out the entire K expression every time, even though we've seen it 100 times? Because I want you to do it. That's why. All right, we get x 0.49 plus x 0.51 minus x. Let's go ahead and make that small x assumption and see if we do better this time. You get 1.8 times 10 to the minus fifth is equal to x times 0.49 divided by 0.51. X is equal to 1.9 times 10 to the minus fifth, and that's, oops, that should be a 1. 1.9 times 10 to the minus fifth, and that makes my pH 4.72. So we do get a small change in pH, right? But it resists that change, right? We didn't say a solution that doesn't change. It just resists that change, right? If we added that same amount to 100 milliliters of water, our pH would have gone down to 2. If we added the same amount to 10 liters of water, our pH would have gone down to 4 from neutral, right? But here we're going from 4.74 to 4.72. Very small change, right? 0.02 change versus several unit changes in water. So we see that a buffer is resisting changes to addition of H+. We'll do examples later on where we see it resist changes to OH-, and we'll see how to do that chemistry as well. It's very similar, except it's a little harder because it doesn't fit directly into our table, because where's OH- on that table? And so we'll see examples of that going forward. But what we found is that the buffer resists changes to pH. All right, so let's go to the general case, right? And what's the general case, right? It's not just where you show a picture of a lovely general. It's where you take things, you say, hey, let's take this kind of concept that we just covered and see if we can write an equation that's easy to use that covers all of our cases. So that's our general case. So we're going to do a generic weak acid, and we're going to do our ice table. And since this is generic, we don't know what our concentrations are. I can't say 0.3, I can't say 0.7. So what I'm going to say is the concentration of HA naught, right? That's our initial concentration. We're not going to do anything with adding H+, adding OH- right now. We're just going to solve the kind of the generic buffer case and see if we can do that. Everything looks the same. Everything looks the same. Right? We're just used to having numbers in there, but now we're putting a variable in there just to say, hey, can we find a way of doing this where we have a different formula so we don't have to do the ice table every time. Ice tables are a little tedious, aren't they? All right, let's substitute that in. Our Ka is going to be H plus A minus over HA, and that is going to be X A naught plus X and HA naught minus X. All right. What do you think? Small x assumption? You're like, I don't know. Didn't you say we have to have a few orders of magnitude difference between Ka and concentrations in order to use the small x assumption? And I did say that. And this general case that we're deriving, you still need to have that, right? It hides it. So this equation that we're deriving is going to hide the fact that you really do still need to verify that your K and your concentration differ by at least several orders of magnitude. But it's a very common thing to do, so I'm going to go ahead and do it. But you do have to keep that in the back of your head. If you have a K of 0.05 and you have a concentration of 0.05, you can't use this generic equation. However, that doesn't happen very often. These Ks tend to be fairly small. Our concentrations tend to be fairly large. So most of the time, this general case works. All right, so let's go ahead and use our small x assumption. We now have that Ka is equal to x times a naught over ha naught. Okay, so that's a nice and easy looking expression. Let's go ahead and solve that for x. X is equal to Ka times, oops, this should have an a minus. All my a's should have an a minus there. Ha naught over a minus naught. All right, so there is a way of doing it. And remember, our x is the concentration of H+. So this expression, Ka times Ha naught over a naught, is our way of getting H+. But oftentimes what we care about is not the H+ concentration, but specifically we just want to know the pH. So we're going to take the negative log of both sides. We get negative log of Ka times H a naught over a minus naught is equal to the log of H plus. And let's go ahead and take the negative log of both sides, which I did on the left but forgot to do on the right. Negative log of that, right? Because that's just going to be equal to pH. Now we're going to use some log rules, right? The log of A times B is the log of A plus the log of B. So we're going to get the negative log of Ka plus the negative log of H, I always do that, I write A first, Ha naught over A naught. But what's the negative log of Ka? That's the pKa. And negative, we can actually put that as an exponent here to the minus 1, because remember the log of A to the n is n log A, so you can do that backwards. N log A is the log of A to the n. So I'm going to take that negative 1 and put it up there. So we end up with a plus sign here, and we get A naught over Ha is equal to pH. Now, I'm just going to rearrange this to write the pH first, because that's how most people write it. pKa plus the log of A naught over A minus. A minus. Why do I keep forgetting the minuses today? Over Ha naught parentheses. Dun, 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 dun. And we have this lovely equation here that allows us to relatively quickly calculate the pH of a buffer solution where the small x assumption works without having to do all that ice table stuff. And this, my friends, is called the Henderson Hasselbalch equation, which is a mouthful, the Henderson Hasselbalch equation, and so most people will call it, or a lot of people, not most people, a lot of people will call it the HH equation. Right? The Henderson Hasselbalch equation is a way of calculating the pH of a buffer solution without having to do the ice table, because you did the ice table when you derived the Henderson Hasselbalch equation. Now, the caveat there is that your concentrations and your Ka values need to be several orders of magnitude difference, because the small x assumption does need to hold. I have never once ever seen a textbook say, you should check the small x assumption after you do this. You should, technically, really, but nobody does. Okay, so just keep that in mind. Don't use this in a case where your K value and your concentrations are very close. But again, that doesn't happen all that often. So it's a pretty safe equation to use. And we're going to use it like crazy. Now, remember, Henderson and Hasselbalch are these two old guys, and they are not the same as Hasselhoff. So this is not the Hasselhoff equation. I've actually had students call it that before. It's not the Hasselhoff equation. It's the Henderson Hasselbalch equation. All right, so it's now your turn. We're going to try to find the pH of a solution made up of 0.35 molar hypochlorous acid, HOCl, where the Ka is 3.5 times 10 to the minus 8th, and 0.115 molar sodium hypochlorite. Now, what I want you to keep in mind, before I let you loose on that, right, is NaOCl. What is that going to do in solution? We know from our solubility rules that it's going to break apart into sodium and hypochlorite. And we know from stoichiometry that we're going to get 0.115 molar Na+, and we're going to get 0.115 molar OCl-. So go ahead and take a look at this problem and see what you come up with. All right, what'd you do? Let's plug it in, man. Henderson Hasselbalch all the way. pH equals pKa plus the log of A minus over HA. Now, how do you know which one's A minus? It's tempting just to be like, oh, this one's got the minus sign, so that's my A minus. But in the case of polyprotics, we might have two different things with minus signs, so you can't look at that. You want to look at who's got the more protons, right? Whoever's got the more protons is the one that's going to give them away. Whoever got the less one is the one that's going to keep them. So here I've got HOCl has 1 proton, OCl- has 0 protons. So it does follow the negative in this case. Now we got to do our pKa, our 3.5 times 10 to the minus 8th. We're going to take the negative log of that, and we get 7.456 plus the log of A minus. We decided that was our OCl, so it's our 0.115 over the concentration of HA, which is 0.350. Those molars are going to cancel out, which is good because you can't take the log of a unit. 7.456. Keep in mind, a log of something greater than 1 is positive. A log of something less than 1 is negative. So we look at that. We have something less than 1, 0.1 divided by 0.3. So it's going to be subtracting from our pH. It's going to be more acidic. Now, in order for it to be more acidic, it means we have more of our acid than we do our base, which is the case. So it's a good double check that you can do is just to think about, did I put that in the right order? Am I getting more basic or more acidic? You're going to get more acidic if you have more of your acid than your conjugate. You're going to get more basic if you have more of your base than your conjugate. All right, so we're going to do that. And when you do that, you get 6.97. Excuse me, 6.97 looks something like that. All right, another one. What is the pH of a solution containing 0.155 molar ascorbic acid and 0.489 molar sodium ascorbate? Right. Hopefully you Henderson Hasselbalch this one, man. pH equals pKa plus the log of A minus. Let's actually write out our A minus and our HA here. Right, and those are our initial concentrations. Never hurts to remind ourselves that it's not equilibrium concentrations, those are initial concentrations. That's what we put into our thing. The pKa here is going to be 4.0969 plus the log of, which one's our A minus, right? The sodium ascorbate is going to be our A minus because if you actually look, right, the ascorbic acid is the acid, the ascorbate is the conjugate. So we're going to put our 0.489 over 0.155. Our molars drop out. We've got a log of something greater than 1, so it's going to add to our pH and make it more basic, which is fine because we have more of our base than we do of our acid. And what you get here is 4.5959, and that's going to round. Since we have 2 digits in our Ka, we get 2 digits after the decimal and a pH of 4.6. So that is how we do our work with the Henderson Hasselbalch equation for simple buffer solutions. What we're going to work on in the future is what happens when we do that. Adding acid, adding base, can we still use our Henderson Hasselbalch equation? Thanks so much. Have a wonderful day.